Electric vehicles make sense, and it's not just the greenwashing. Let's look under the bonnet from an engineering perspective. To do this, we need to appreciate today's internal combustion engine cars, as they are the result of over 100 years of research and development. Very sophisticated, technologically advanced computerization for optimum performance in all conditions, including speed, temperature and even air quality. The modern internal combustion engine technology has led to a vast array of engine types, from the high revving performance machines to powerful diesels. The performance of these engines is measured by their power and torque. Here is a graph showing the power and torque of a typical internal combustion engine. The torque, the turning force, is measured as Newton meters, is the product of the force Newton and the length of the lever in meters. Concentrating on the torque curve, we can see two main things. One, the motor must be running to produce torque, and two, the torque varies with the speed of the engine. Let's talk about point one, the motor must be running. The issue here is when the vehicle is stationary, how do you engage a rotating engine? Two main methods are by clutch or torque converter. So humans, being very inventive, found methods of engaging a running engine to drive a vehicle from standstill. Problem solved. The second challenge was harnessing the torque as it varied with the engine speed. Sufficient torque is initially required to start the vehicle moving to overcome the inertia. To achieve this, the engine is connected to the vehicle wheels using reduction gearing. Reduction gearing reduces rotational speed and increases the torque. Once engaged, the engine speeds up, moving the vehicle. However, the vehicle speed will be limited as the engine has its speed limit. We now want to sacrifice torque for rotational speed. The reduction gear, which is fine to initiate movement, is now restricting the vehicle's speed. A different gear ratio is needed to rotate the wheels faster at a lower engine speed. Hence, the gearbox was invented. The gearbox was also required to enable a vehicle to go backwards, reversing, as the internal combustion engine only rotates in one direction. This diagram shows the relationship of the vehicle speed to the individual torque curves of each gear. The ultimate being an overall smooth torque curve from standstill to highway speed. Modern gearboxes go a long way to achieve this smooth torque curve, some having even 7 gears to achieve this. They utilise sophisticated technology to manipulate multiple gears and clutches seamlessly. To recap so far, 100 years of research and development on the internal combustion engine driven vehicles has given us what is probably the ultimate outcome for the internal combustion engine and associated gearbox. Now, using the same measure of performance, we can compare the internal combustion vehicle to an electric vehicle. Here is the typical power torque curve of an electric motor. The first difference to the internal combustion engine torque curve is that it has torque from 0 RPM. That is correct. A stationary electric motor can produce torque. If you hold the chuck of a variable speed drill and slowly pull the trigger, you'll feel the torque while there is no rotation. Having torque available at 0 RPM means the vehicle does not need a clutch or torque converter, a big saving in components, complexity, weight and maintenance. The second observation of the torque curve is that it is relatively flat up to maximum power, and this is over a wide speed range. Because of this, most electric vehicles do not need a gearbox, just a suitable reduction gear. Reverse gear is also not required, as electric motors can change direction of rotation. So what does this all mean from an engineering perspective? It appears the ultimate goal of an internal combustion engine vehicle is to have torque from standstill and smooth torque through to highway speeds. What it is striving for turns out to be the basic attributes of an electric motor. All the complexity of today's internal combustion engine and gearbox can be achieved by a relatively simple electric motor. You may say, well, if so, why has the internal combustion engine dominated for the past 100 years and still is? Well, electric motors may have lost out on the road transport market, but electric motors have impacted almost every aspect of your life. Even your car, an electric motor is essential to start it. Wind up the windows, adjust your seat. Electric motors have the torque to pull kilometres of train wagons, to propel very fast trains, to run your fridge and air conditioner, automatic doors, wipe your windscreen, industrial conveyor belts to printers, building lifts to clocks. I'm sure you could list plenty more. So over the past 100 years, electric motors and power electronics have advanced significantly. Hence, from an engineering perspective, I conclude that the best propulsion for road transport is the electric motor. This is a Kodak moment for the vehicle industry. Kodak had a highly refined process and procedures for developing photos. You could drop your film off at a convenient location and often have the developed photos the next day. Kodak automated the complex chemical process and maximised efficiencies in the delivery. But with a digital camera, you don't need complex chemical processing and you get instant viewing. I see similarities here as the complexity of the internal combustion engine and gearbox can easily be achieved by an electric motor. A Kodak moment is happening. The electric motor vehicle is superior in other ways as well, including minimal maintenance, regenerative braking, quiet, no harmful fumes. Like Kodak, the ICE vehicle days are numbered. The internal combustion engine will still be useful for applications such as generating electricity, but not to power vehicles. In conclusion, I hope you can see why electric vehicles make sense from an engineering perspective.